Welcome back to AI Talks with Chris and Nita. We've got a fascinating topic for our deep dive today. Our listeners have sent in a ton of research papers on DBSCAN. Looks like they want us to break it down.
DBSCAN, definitely one of the more interesting clustering algorithms out there.
It is, and we're going to really get into it today, so get ready.
Absolutely.
So for anyone just tuning in, DBSCAN stands for Density-Based Spatial Clustering, and it's used in all sorts of fields: marketing, fraud detection, even astronomy. Basically, anywhere you need to find patterns in data. But the thing that makes DBSCAN special...
You're talking about how it can find clusters of any shape.
Right. And it can handle those messy data sets with outliers, the kind of stuff other clustering algorithms trip over.
Exactly. A lot of real-world data isn't nice and tidy, Think about, mapping the spread of a disease. You're not going to get perfect circles.
Yeah. It's like those star clusters in the night sky. Some are packed together in a constellation, but you've got all these other stars scattered around.
Perfect analogy. And DBSCAN can tell which stars belong to a constellation and which ones are just out there on their own.
So how does it actually deal with that? Imagine you're a detective, right? Trying to map out where a bunch of suspects hang out. You've got their location.
Okay, yeah.
Could something like k-means clustering handle that? I mean, you might have some suspects clustered in one bar, some at another.
Well, k-means works best when you've got these well-defined, roundish clusters. But what if your suspects are meeting up in, like, a long, narrow alleyway? Or scattered across a park? K-means would struggle with that.
And DBSCAN wouldn't, because it doesn't assume any particular shape for the cluster.
Exactly. It lets the data speak for itself.
Okay, but how does it know what's a cluster and what's just random noise? The research mentions these two key parameters, epsilon and minimum points. Those seem important.
Definitely. Think of epsilon as, like, our detective's search radius. How close do two suspects have to be to consider them connected? If they're within epsilon of each other, they could be part of the same group.
Ah, I see. So epsilon defines what close actually means.
Right. And then minimum points. That's how many suspects our detective needs to find within that search radius before they say, okay, this is probably a real hangout spot.
So it's not enough to be close. You've got to have enough friends nearby. Like, okay, if our detective finds one suspect in a coffee shop, that doesn't mean much. But if they find 5 suspects...
Exactly. That's when it starts to look like a pattern, right? And those suspects become what DBSCAN calls core points.
Core points are like the seeds of a cluster.
Exactly. And from there, DBSCAN starts to chain things together. Any other suspect within epsilon of a core point gets pulled into the cluster, and any suspect near those suspects, and so on.
So as long as there's this dense chain of points all within epsilon of each other.
They all become part of the same cluster, even if the overall shape is, like, totally weird and irregular.
It's almost like connecting the dots, but the lines can only go through dense areas.
I like that. And what about those loner suspects who are just out doing their own thing? DBSCAN labels those as noise.
Which is actually really helpful, right? In the real world, not every data point has to belong to a cluster. Some things are just outliers.
Exactly. And DBSCAN is fine with that. It doesn't try to force everything into a group.
The research also mentions that DBSCAN works really well with high-dimensional data, the kind of stuff we can't easily visualize.
Right. Like with fraud detection, you might have dozens of variables: purchase amount, time of day, location, way too many dimensions to wrap your head around. But DBSCAN can still sift through that data and find those hidden clusters of fraudulent activity.
Powerful stuff. So just to recap, DBSCAN handles any cluster shape, it deals with noise, and it works in high dimensions. What's not to love?
Right. It's a really versatile algorithm.
And it makes you think, right? Like, where else could we use an algorithm that's good at spotting hidden groups? Beyond fraud detection, beyond marketing.
That's a great question. Like, what about in urban planning? Maybe DBSCAN could help identify areas where there's a high density of, say, traffic accidents, or in public health, finding clusters of disease outbreaks.
So many possibilities. Like, DBSCAN give us this new way of looking at data, seeing patterns that we might have missed before. And that's it for our deep dive on DBSCAN. Hopefully this gave you some ideas to chew on. We'll see you next time.